Hello, I'm Shreya Gupta presenting a report on Hermite polynomials, Laguerre polynomials, moment of inertia matrix and rocket dynamics using Lagrange and Hamiltonian mechanics as a part of Science 1 project. First, I will discuss about Hermite polynomials. Hermite polynomials are set of orthogonal polynomials which are defined from minus infinity to plus infinity. Basically we have two types of Hermite polynomials, that are probabilist Hermite polynomials and physicist Hermite polynomials. Probabilist Hermite polynomials are defined by Hen of x, that is equals to this complex function, and similarly physicist Hermite polynomials also have a complex function. Basically both these Hermite polynomials are rescaling of each other. They are not exactly identical, but they are also not exactly different. They are just rescaling of each other. Hermite polynomials we obtain from as a solution of Hermite differential equation. Probabilist Hermite polynomials have a differential equation of this type. Any differential equation of this kind give us probabilist Hermite polynomials, or simplified form of this Hermite of this differential equation is this thing: u double dash minus xu dash equals to minus ku. This equation gives us a solution uniquely. And similarly for physicist Hermite polynomials, we have differential equation of this kind where k is a constant and solutions are uniquely given by u of x equals to hk of x. Now we will discuss about generating functions. Hermite polynomials have generating function. Generating function is a power series whose coefficients give us the sequence. For probabilist, we have generating function e raised to the power xt minus t square by 2. And for physicist, we have generating function 2xt minus t square. In the expansion of these functions, the coefficients of t raised to the power n divided by n factorial give us the Hermite polynomials. Now come to contour integral representation. Contour integration is a method of evaluating certain integrals along paths in the complex plane. For probabilist polynomials can be defined in terms of contour integrals as this equation, which is a which is a function of contour integral of generating function of probabilist polynomials. Similarly, physicist polynomials include contour integral of generating function for physicist Hermite polynomials, where contour encircles the origin. Hermite polynomials have many properties. One of them is orthogonality. For probabilists, we have weighting function e raised by minus x square by 2, and for physicists we have weight function e raised to the power minus x square. uh, if we take two Hermite polynomials and integrate them over minus infinity to infinity with their weight function, and for m not equals to n, we take two different Hermite polynomials, then their integration is 0. But for same if m equals to n, like for same polynomial, we get this function for probabilist and this function for physicist. Probabilist polynomials are thus orthogonal. Stop. We have a second property, recursion relation of Hermite polynomials. We can get n plus 1th term of Hermite polynomial by a function of as a function of nth term or n minus 1th term. Like for probabilists, n plus 1th term is equals to x into nth term minus n times of n minus 1th term. By using recursion, it is easier to get to further, like n plus 1th or n plus 2th term we can get easily. Hermite polynomials have one more property, symmetric. That is, they are symmetric about x equals to 0. So hn of minus x equals to minus 1 raised to power n hn of x, and similarly for probabilists also. So we can say Hermite polynomials is an even function if n is even, and Hermite polynomial is an odd function if n is odd. One more property of probabilist Hermite polynomials is expected values. Hermite polynomial is if we have a random variable x that has expected value mu, then then hen of x also has expected value un. One most important characteristic of Hermite polynomials is they are the solutions to the radial part of Schrodinger equation. So they are connected with quantum harmonic oscillator, and Schrodinger equation is defined with this equation, where xi is the state of particle and v of y is the potential energy and E is the total energy. So if we assume potential energy to be equals to y square, or and y equals to kx, that is potential energy equals to k square a square, and we substitute this in this equation, then we and differentiate it with respect to x, we get this equation where b is of this form. Now this is a second order differential equation. If you consider equation of this kind, xi double dash minus x square xi equals to minus xi, then it has a solution of e raised power minus x square by 2. So similarly for this kind of equations, we can get solution which is of the form e raised power minus x square by 2 into h of x, where h of x denotes a Hermite polynomial, and it is a function that we need to determine. Uh, for different values of n, for we have different values of b, and similarly we get different Hermite polynomials. This is what I want to tell about Hermite's polynomials. Now we'll come to Laguerre polynomials. Laguerre polynomials are the solutions of differential equation of type xy double dash plus 1 minus xy dash plus ny equals to 0. And for generalized Laguerre polynomials, we have one more term a y dash, and it is true, it will give Laguerre polynomials only if a is greater than 0 and n is greater than equals to 0, that is n is non-negative. uh, there are many formulas by which we can define Laguerre polynomials. One of them is Rodriguez formula, by which we can define Laguerre polynomials like this and this, and similarly generalized Laguerre polynomials can be defined as this. There is one more form we can define Laguerre polynomials, that is closed form. We can define closed form Laguerre polynomials in closed form as this, where x is less than infinity but greater than equals to 0. That is the most important condition. And similarly there is a closed form for Laguerre generalized Laguerre polynomials also. And negative polynomials with negative index can be defined as ln L of minus n x equals to e raised power x ln minus 1 of minus x. And we have generating function for Laguerre polynomials that is defined as this, and for generalized polynomials it is this. Like Hermite polynomials, we have contour integral representation of like Laguerre polynomials, which is defined as this, and it is also a function of their generating function. Now the properties of Laguerre polynomials. First property is orthogonality. similar to Hermite polynomials. Here also, uh, the weighting function for Laguerre polynomials is e raised by minus x, and they are orthogonal over 0 to infinity. For n equals to m, they are equals to del mn, and for m not equals to n, their integration with weight function with respect to x is equals to 0. Recurrence relation, we can get n plus 1th term uh, uh, after finding nth and n minus 1th term. One more property of Laguerre polynomials is that they have a orthonormal function, that is phi x equals to e raised by minus x by 2 into ln x. Now, one most important thing is there is a relation between Laguerre polynomials and 3D Schrodinger equation. Schrodinger, we know that Hamiltonian operator into xi equals to e xi, where Hamiltonian operator is this, where e square by r is potential energy. On solving this equation and putting uh, L square operator, we get this function. And now putting the eigenvalues of L square, which are uh, L, L into L plus 1, we get this function. And here we use xi equals to uh, r of r into y theta of theta. We break a xi into radial part and spherical part, and by this we get the solution for radial part as this complex function where n and l is a normalizing constant, which is equals to this function. Now I will discuss about moment of inertia matrix. Moment of inertia matrix is rotational analog to mass, and it is a mass moment of inertia is about a fixed axis. About a fixed axis is a property of a body that measures body's resistance to rotational acceleration. It is a tensor quantity, and it determines the torque needed for a desired angular acceleration about a rotational axis, and it is an additive property. So a moment inertia of a composite system is the sum of moment inertia of its component subsystems. And for bodies free to rotate in 3D, their moments can be described by a 3 cross 3 matrix, which is defined as inertia matrix, uh, as shown here. And inertia matrix has elements which are scalar moments of inertia, and it is inertia matrix is very useful for the calculations of angular momentum, kinetic energy, and resultant torque. And very important application of inertia matrix and Newton's laws of motion is analysis of spinning top. Suppose if we consider a system of n particles which have different positions, whose positions are denoted by ri and velocity is denoted by vi, and we take a some point capital R, and their positions relative to that point be del ri, and their velocities with respect to that, and their velocities, absolute velocities, can be defined in terms of del Ri as a function of this Vi equals to omega into del Ri plus Vr, where omega is the angular velocity of the system and Vr is the velocity of R point that we selected. Now moment of inertia can also be as described as the inertia tensor, and inertia tensor is constructed from 9 components, uh, each of which component is formed from this matrix, this summation. Suppose we have an inertia matrix of this type. Now we can consider, suppose ix's, iyy and iz are the moment of inertia about its 3 axes, and product of inertias in two different axes are given by ixy, ixz and iyz. Ix's we can obtain as this function, and similarly iyy and izz, and similarly we can obtain ixy, ixz and iyz. This inertia matrix is symmetric, so I12 is position equals to I21 is equals to ixy, and I13 element equals to I31 element equals to ixz. Similarly I23 equals to I32 and it equals to iyz, and I11 equals to ix's, the moment of inertia of 3D body about x-axis, and I22 equals to inertia, moment of inertia of the body about y-axis, and similarly I33 is the moment of inertia of the rigid body about the z-axis. And we know that IC is a symmetric matrix. We can define IC as a whole as a as in so we can define IC inertia matrix in terms of these elements. As we discussed earlier that this it that we can that inertia matrix is very important for the calculations of angular momentum, kinetic energy and resultant torque. So we take an example of angular momentum. Angular momentum is defined for the discussed system B sigma equals to 1 to n for n particles, B mi into del ri cross product with vi, which can be defined as this function where and finally it can be given by inertia matrix into omega, where inertia matrix is given by this. Now if we consider one case that uh, angular momentum is parallel to omega, then uh, L equals to omega, and by this function, and we know that L equals to IC inertia matrix into omega, then we can say that IC into omega equals to lambda into omega, and if we solve this equation, we take its determinant, then we'll find this equation where I is the identity matrix, and we find three eigenvalues of lambda. These three eigenvalues of lambda will give us eigenvectors uh, which are they give us the values of omega, which are the eigenvectors, and these eigenvectors are orthogonal. Thus this matrix makes so using an inertia matrix makes the problem easier. It makes calculations easier. It helps us to find angular momentum and kinetic energy and many more things. Now we will discuss about rocket dynamics using Lagrange and Hamiltonian mechanics. So first we will discuss about rocket. Suppose this is the rocket and it has mass m. It is going up with a velocity v, and it has some external force is acting on it, and consider dm mass that of the gases that ejects from it at a time instant t. It has velocity v at time instant t plus dt, t plus delta t. Some dm mass will be ejected with some velocity c, and then its velocity will become v plus dv, and the thrust uh, the dm mass will exert an impulsive force on the rocket, and similarly rocket will exert an impulsive force on the dm mass. The thrust force acting will be equals to c into dm by dt, and in this case Lagrangian equals to, we know that Lagrangian equals to t minus u, where u is mgx and t is half mv square, which is v is the velocity of the rocket, m is the mass of the rocket at that instant time, and x is the position of the rocket at the time at t instant. Then but here generally we see that d by dt dou L by dou Q dot min equals to dou L by dou Q. But in this case uh, uh, um, but this is true only when all the forces can be expressed in terms of potential, but this is not the case here. So thrust of the exhaust cannot be expressed in terms of potential, so we have to use this function. There will be a 1 minus f force will be there, and this f force is a force exerted by exhaust on the rocket. And when we calculate dual by we will calculate dual by dou v and dual by dou x, and when we put this in this equation, we get this equation. And similarly when we do Hamiltonian, we'll use total momentum of the system as mv, that is the rocket momentum of rocket, minus momentum of dm mass, where v minus c is the relative velocity of the dm mass with respect to the rocket. And thus we calculate dou h by dou x and dp by dt and equate them, we get the same equation. This is the equation of motion for rocket.